So in this video, we are going to be talking about planes. Much like the video that we had on lines, we're going to be talking about expressing planes in three different ways. So there's a lot of parallelisms between this one and the video on lines. So without further ado, let's jump in. A line, it turns out, is determined by either 2 points or a point and a direction. So, for example, let's say we have this point right here and this point right here. Then there's only one line that can be drawn on these 2 points. That line. Alternatively, we could just start with a single point and then point in a single direction. Let's say that direction. And then that determines a very unique line. There's only one line that can be drawn on that point pointing in that same, or in that particular direction. So it takes two quantities, either 2 points or a point and a direction, to determine a line. On the other hand, if we wanted a plane, then it turns out it actually takes 3 different quantities. So we could have 3 different points. If we have a single plane and they have 3 different, or if we have 3 space and we have 3 different points in space, then we can draw a single plane on those 3 points. There are certain situations in which that can't be done, but we won't worry about those. They're very specific. Or if we have a single point and 2 different directions, much like this picture, so we have our single point and then the 2 different directions, then that determines a plane. On the other hand, instead of having 2 different directions and a single point, we could actually replace those 2 different directions with a single direction. But that direction actually isn't going to be a direction on the plane. It's going to be a direction that is orthogonal to the plane. So if we actually have a single point, and then we find an orthogonal direction to the plane, then we can actually express this plane in terms of just these 2 quantities. Because this takes the least amount of information, having a point and a single direction, we're going to be dealing with this particular way of expressing a plane. Let's express a plane as a point on the plane and a direction orthogonal to the plane. So we actually have a word for a vector that's orthogonal to a plane. We call that type of vector a normal vector. A vector n orthogonal to any particular plane P is called a normal vector to P. So that leads us to our first way of expressing a plane. Let's say we have a point Q. Q is x naught, y naught, z naught. This is some point in the plane. So if we're looking at our picture here, then Q would be this point right here, a point in the plane. If P, which has coordinates x, y, z, is some arbitrary point in the plane, and r naught is the position vector for our point Q. If we come in here, let's move this label Q. Q is going to be right here. R naught will be this vector from the origin up to that point. And let's say we have some other point. Let's say this is P, which has coordinates x, y, z, and r, we're going to call that the position vector for P, which has coordinates x, y, z. Then a vector in the plane, which we can call QP, is given by r minus r naught. So QP, this will be the vector that starts at Q and goes to P. This is the vector QP. This is a vector. QP is in the plane. And QP has a representation. We can write QP as r minus r naught. If we look at our triangle here, then we have r is our vector over here, Q, R naught is our vector here. And if we look at the subtraction of R minus R naught, then we get the vector QP. So R minus R naught actually has components X minus X naught, Y minus Y naught, and Z minus Z naught. So there's no definition here just yet. We're just lining up all of these particular different vectors and noticing that the vector QP, which can be expressed by R minus R naught, which has components X minus X naught, Y minus Y naught, Z minus Z naught. This is a vector in the plane. Now let's say we have the vector n, and n has components a, b, c. And this is a normal vector. So here, this is the vector n. Then we know that the vector n is orthogonal to the vector qp, which is r minus r naught. This equation must be true. If we use our dot product properties, we can distribute the dot product, and we can get n dot r minus n dotted with r naught. This is equal to 0. All these are vectors. 0 is a number, though. We can add n dot r naught to both sides to get n dotted with r is equal to n dotted with r naught. That's this second equation right here. Each of these equations is called a vector equation of the plane. This is a true relationship. This is called a vector equation. So here's our first way to actually express the equation of this plane. It's in terms of vectors, and if we have some of this information, it's a really nice, clean way to express the equation of a plane. It's a single equation. This is actually usually the more common one. N dotted with r minus r naught is equal to 0. This is called a vector equation of the plane. Now, we actually move pretty quickly to get to the second way to express the equation of a plane. Because n dot with r minus r naught is equal to 0, and if we just replace all of these vectors with their components, well, n is a, b, c. R minus r naught is x minus x naught, y minus y naught, z minus z naught, as defined right up here. And now we know something about dot products. If we dot ABC with x minus x naught, y minus y naught, z minus z naught, then we get a multiplied by x minus x naught, b multiplied by y minus y naught, c multiplied by z minus z naught. Add those all together, we get 0. So there's nothing new that we're introducing here. We're just expanding this vector equation. This last equation here isn't in vector form. It doesn't have any vectors associated with it, but it does have the different directions. A, B, and C, these are the directions. They're not the direction pointed for the plane, but it's for the directions orthogonal to the plane. X naught, Y naught, Z naught. These are associated with any particular point in the plane. And so we have our point, we have our orthogonal direction. This single equation actually holds all of the information necessary to determine a plane. And we call this the scalar equation of the plane. And that's our definition right here. The equation A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0 is called the scalar equation of the plane through Q with normal vector A, B, C. There's a lot of information there, but and there's a lot of words in this particular definition, so a lot of times people just say scalar equation. Let's take a moment to actually work with these two definitions. Let's find both the vector equation and the scalar equation of the plane through the point 1, 2, 3 with normal vector n, which is 2, negative 1, 5. After that, we'll actually try to find the intercepts of this plane and then sketch the plane. So, if we want to find a vector equation, then this means that we need a normal vector. And what else do we need? R minus R naught. Now, the normal vector n is given right here, so all we need is r minus r naught. R minus r naught is the vector x minus x naught, y minus y naught, z minus z naught. This is a vector. Now x naught, y naught, z naught, that represents any point in the plane. We know that 1, 2, 3 is a point in the plane, so we can actually write this as x minus 1, y minus 2, z minus 3. Here's a vector that's actually in the plane. Here's a representation of the vector r minus r naught. So, if we're looking for a vector equation, there are two different forms. I know I have a preference for n dotted with r minus r naught equals 0. This is called a vector equation for the plane. Our vector n is 2, negative 1, 5. And r minus r naught is x minus 1, y minus 2, z minus 3. This is equal to 0. This is known as our vector equation. In order to find our scalar equation, then we take our vector equation and we actually work out the dot product. If we take the dot product of 2, negative 1, 5 with x minus 1, y minus 2, and z minus 3, then we get 2 times x minus 1 plus, or rather minus in this case since our second component of n is negative, minus 1 times y minus 2 plus 5 times z minus 3. That's equal to 0. That's simply working out this dot product. Now this actually gives us our scalar equation, and this is it. There's our scalar equation, there's our vector equation. They're simply a step apart from each other, and they both represent equations that would give us this plane. Now it says find the intercepts of the plane and then sketch the plane. The intercepts of the plane, this is a way of saying find where the plane intersects the x, y, and z axes. This is how we find the different intercepts. So in order to find the x-intercept, then we need something that's going to give us something on the x-axis. Points that are associated with the x-axis have y-coordinate and z-coordinate both 0. So if we want to find a point on the x-axis, then this means that we need to let y equal 0 and z equal 0. So the x-intercept is found by taking our equation, 2 times x minus 1, minus 1 times y minus 2, but y is 0 in this case, plus 5 times z minus 3, but z is 0 in this case. And we have a single equation here in a single variable. We should be able to solve for x. Writing this out, we get 2x minus 2 minus negative 2, so that's plus 2, plus 5 times negative 3, so that's minus 15, which tells us that 2x equals 15, or that x is 15 halves. For our y-intercept, we do the same thing, except x is 0 this time, y is just y, and z is still 0. Multiplying all of this out, we get negative 2 minus y plus 2 minus 15 equals 0. So that y is negative 15. Lastly, a z-intercept. This is found when x is 0, when y is 0, and when z is arbitrary. Multiplying this out, we get negative 2 plus 2 plus 5z minus 15 equals 0, or rather, when z is equal to 3. So, the x-intercepts are going to be 15 halves. Alright, the x-intercept is at 15 halves. The y-intercept is at negative 15. And the z-intercept is at 3. Now we actually want to sketch this. So in order to sketch our plane, it's kind of a difficult thing to do, sketch a plane on a plane. So this is going to take a little bit of creativity and a little bit of ingenuity, but we always start out in the same way. Actually draw our axes. So here's the positive x-axis, here's the positive y-axis, and here's the positive z-axis. Then one of the better ways to sketch a plane, or one way to sketch a plane, is actually to plot the different intercepts and then kind of connect them like a triangle. So the x-intercept is at 15 halves, so come in here and say this is representing 15 halves. And then the y-intercept is at negative 15, so this is going to be 15 behind the origin on the y-axis, so let's call this negative 15. Z-intercept is at 3, let's call that 3. Then one way to graph this would be to connect these 3 intercepts and think about this as a plane intersecting the corner of a room. So we have what looks like a kind of tilted triangle here. That would be like if you just all of a sudden started walking toward the corner of a room and then there was just this slight incline toward that corner. One of the best ways to represent that this is a solid surface is to first have all 3 of these intercepts and then have these boundaries, then kind of shade in here. So if we shade this particular region, it looks like this is lifted up off of the origin, off of the XY plane. To represent that this is not just a triangle and that this keeps going, we will usually extend these line segments to actually say, hey, these actually do keep going. These don't just stop here, but this is what our plane would look like. In this particular octant, it looks like this triangle, but these line segments say these do extend beyond. If you would like, you can even shade a little bit around it. But here's a representation of our plane. All right. So this is a way to actually write down a vector equation of a plane, scalar equation of a plane, finding the intercepts of that particular plane, and then sketching what the plane might look like. Now, if we actually expand this scalar equation, if we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. This is equal to 0. Let's say we expand this out. So if we multiply a, we get ax minus ax naught. Multiply b in, we get by minus by naught. Multiply c in, and we get cz minus cz naught. And if we rearrange these, now x is a variable, y is a variable, c is a variable. A, b, and c are just numbers. X naught, y naught, c naught, and z naught are all numbers. So AX is actually a term with a variable. BY is a term with a variable. CZ is a term with a variable. But AX naught, BY naught, CZ naught, all of these are constants. If we combine all of these together into a kind of a big constant, let's call with the negatives, let's call this just D, then we can actually rewrite our equation as AX plus BY plus CZ plus D. On the right side, it's still equal to 0. Then we get a new form of our equation. This last equation here is called a linear equation. So we have the vector equation as one way of representing our plane. A scalar equation is another way of representing our plane. And this last linear equation is the third way that we're going to talk about representing a plane. Any equation that has this form, AX plus BY plus CZ plus D is equal to 0. This is called a linear equation in X, Y, and Z. And it turns out, if A, B, and C are not all 0, then the linear equation represents a plane with normal vector ABC. Now, for example, if C was equal to 0, then this equation would probably look a lot more familiar. If C was equal to 0, then this term wouldn't really be here. And we would get AX plus BY plus D equals 0. This can really be manipulated into a form of Y equals MX plus, I'm going to call it capital B, just to represent this bigger, different from this little b, which isn't a plane. But this came from a plane. So it actually turns out that this particular expression is going to represent a plane when A, B, and C are not all 0. If one of them is equal to 0, then it might represent a plane, but it's a little bit harder to see that because we wouldn't see a third variable. We would only see two variables. So it really depends on your perspective and how you are viewing this particular equation. Most of the time, though, you're going to have A, B, and C all being non-zero. So let's try a third example. We're going to have the exact same setup. We have this point, P, which is 1, 2, 3. We have this normal vector, N, which is 2, negative 1, 5. Let's find a linear equation for this plane, and then graph this plane in GeoGebra. Now we already have two other equations for this plane right up here. We have a vector equation, we have a scalar equation. Now in order to actually get the linear equation, all we did is we took our scalar equation and we just multiplied everything through. So let's try that. Our scalar equation is 2 times x minus 1 minus 1 times y minus 2 plus 5 times z minus 3 is equal to 0. If we multiply everything through, we get 2x minus 2 minus y plus 2 plus 5z minus 15 is equal to 0. And if we combine all of our like terms, then we end up with 2x minus y plus 5z. We have a negative 2 and a positive 2. Those eliminate each other. We're just left with a minus 15 is equal to 0. Here's the equation. Here's a linear equation for our plane. Let's graph this in GeoGebra. So we come into GeoGebra. We can go into the GeoGebra Classic app. And then over here, when it loads, we want to hit the 3D calculator. So let's double check with our equation. So we have 2x minus y plus 5z minus 15. 2x minus y plus 5z, what was the last part? Minus 15 is equal to 0. All this other stuff just kind of auto-loaded. We'll talk about that in a later video, but here we go. 2x minus y plus 5z minus 15 equals 0. And here's a representation of our plane. We can kind of shift this around. We can see that this actually does intersect the z-axis right up in here. If we were to zoom out, we could see that it intersects. Looks like this is the x-axis down here. And looks like it would probably intersect the y-axis somewhere back in this particular region. But here's our plane. What's nice is that this plane is actually typically easier to graph than lines in 3 dimensions. And all of our different representations of our plane always included just a single equation, so we're not trying to include multiple equations into a single bar. Here, it works out really nicely. Alright, here's our linear equation for the plane through the point 1, 2, 3 with normal vector to negative 1, 5. Alright. Let's actually combine information about these planes with some stuff that we've actually dealt with before, with lines. Turns out if we have a line and we graph that line and that line is not in the plane, then the line will intersect the plane, if it intersects it, in a single point. So that's what this example has to deal with. Let's find the point at which the line, with parametric equations given here, let's find the point at which this line intersects the plane. 17x plus 11y plus 8z minus 63 is equal to 0. Alright, so we're already given an equation of this plane. Here's this plane given in its linear form. And we have relationships for x, y, and z. Now in order to find the point at which the line intersects the plane, we want some sort of a relationship that involves all of the information about the line as well as the plane. So we want to take all of the information for this line and plug it into the equation that involves the plane. We know that x is 1 plus 2t, so let's replace that x there with a 1 plus 2t. We know that y is 3 minus t, so let's replace this y with a 3 minus t. We know that z is negative 4 plus 5t, so let's replace that z with a negative 4 plus 5t. And nothing else changes. Now, big thing to notice between these two equations is that the first equation that was printed is in 3 different variables, and the second equation that we just wrote out is in a single variable. It's in our parameter, which means that we can actually take this equation and we can solve it for our parameter. We just need to multiply everything out. 17 times 1 plus 2t, that should turn into 17 plus 34t. 11 times 3 minus t is 33 minus 11t. 8 times negative 4 plus 5t should give us negative 32 plus 40t. And we're subtracting 63. Now we need to combine all of our like terms. We have 34t, and negative 11t, and 40t. Those 3 together should combine to give us a single amount of t's. 17, 33, negative 32, and negative 63. Those should all combine together to give us a particular constant value. Alright, so this should come to, looks like 63t minus 45 is equal to 0. From this equation, we can solve for t. If we add 45 to both sides and divide by 63, we get t is 45 over 63. We should always simplify our fractions. I know that 3 goes into both of these, so t should be 15 21st. It looks like 3 still goes into that, so it looks like t should be 5/7. Now simplifying this fraction really just makes it a lot easier when we plug this particular value back into our x, y, and z values from above. So we should be able to plug it in here, here, and here. We are looking for a point, which is an order triple x, y, z. X is 1 plus 2 times 5/7. Y is 3 minus 5/7. And z is -4 plus 5 times 5/7. Now 1 plus 2/5, that's going to be 1 plus 2 times 5/7 is going to be 1 plus 10/7. That's going to be 17/7. 3 minus 5/7 is going to be 16/7. And -4 plus 25/7 is going to be -3/7. And here is the point at which our plane and our line actually intersect each other. Alright, so we've just covered a lot of information, so I want you to take a few moments, pause this video, and see if you can work through and find, for the plane described here, a vector equation, a scalar equation, a linear equation, so all 3 of those different forms of the equation for a plane. Find the intercepts of this plane and sketch it by hand, and then find the point at which the line, whose vector equation is given right here, intersects the plane. And then try graphing this, just to see if this actually looks accurate. One last thing before you go into this. Please note that this symbol right here looks like a pi, is a pi. It's the capital pi. We already have a point here, p, and so we just want to name this plane kind of the Greek version of p, which is pi. Lowercase pi is typically reserved for our constant that we're used to seeing, so just going for an uppercase pi here. Pi for p for plane. So find all of this information about this particular plane. Alright, so you've tried that out. This particular exercise does go through a few more steps because all I've given you and all you've been given here is 3 points in the plane. So you haven't been given a normal direction here, so we actually have to come up with that direction. So if you remember from the cross product video, the way to find a normal direction to a plane is to take 2 vectors within that plane and then cross them. So we have 3 points, P, Q, and R, so let's come up with 2 vectors. Let's let U be the vector PQ, and let's let V be the vector PR. Now PQ, that's going to be the vector taking 2 minus 1, which is 1, -1 minus 2, which is -3, and 5 minus 3, which is 2. So there's our vector U. V is the vector PR, so it's going to be with an x component of 4 minus 1, which is 3, 1 minus 2, which is -1, and -2 minus 3, which is -5. So now we need to take these 2 vectors, PQ and PR, U and V, both of these are actually in the plane, so we need to cross them to get a vector that's normal to the plane. So N is going to be the vector U crossed with V. Now, from the cross product stuff, we know that we can take the vector U, 1, -3, 2, and the vector V right beneath it, 3, -1, -5. And then write those vectors again right next to it. 1, negative 3, 2. 3, negative 1, negative 5. And then cross out the left side and the right side, and then start doing our crossing. Here's our cross for I. Here's our cross for J. Here's our cross for K. And finding these 2 by 2 determinants, we get negative 3 times negative 5 is positive 15. Minus negative 1 times 2, which is going to be plus 2. That's how many i's we have. 2 times 3 is 6. Minus negative 5 times 1 is 6 plus 5. That's how many j's we have. And then 1 times negative 1 is negative 1. Minus 3 times negative 3, so it's going to be plus 9. That's how many k's we have. So n ends up being the vector 17, 11, negative 8. Or sorry, this is actually a positive 8. So this is a vector, n, that is normal to our plane. If we want to find a vector equation, then the vector equation has the form n dotted with r minus r naught is equal to 0. Now n is the vector 17, 11, 8. So we have 17, 11, 8. We're dotting this with r minus r naught. R is x, y is z. R naught can be any of p, q, or r. Just for simplicity, let's just choose p, because that's the point 1. And then y minus 2. And then z minus 3. That's equal to 0. Here's our vector equation. Now we need our scalar equation, so we just need to multiply this dot product out. So we have 17 times x minus 1 plus 11 times y minus 2 plus 8 times z minus 3. That's equal to 0. This is our scalar equation. In order to get our linear equation, we multiply this out even more. We get 17x minus 17 plus 11y minus 22 plus 8z minus 24. That's equal to 0. Alright, so now if we simplify this, we should get 17x plus 11y plus 8z, and then negative 17, negative 22, and negative 24 end up being minus 63. And this actually looks kind of familiar. Here's our scalar equation, and, well, that's actually the exact same scalar equation we had here in example 3. Which is kind of nice. Part D says let's find the intercepts of this plane. So the intercepts of this plane are found by letting x and y be 0 to find the z-intercept, letting x and z be 0 to find the y-intercept, letting y and z be 0 to find the x-intercept. So for the x-intercept, this is letting y and z both be 0, so we get 17x minus 63 is equal to 0. So that we get x is 63 17ths. To get a y-intercept, we want to let x and z be 0, so that we get 11y minus 63 equals 0, so that y is 63 elevenths. And to find the z-intercept, we let x and y be 0, and so we get 8z minus 63 equals 0, so that z is 63 eighths. When we sketch this, we need to start with our axes. So here's z-axis, Here's a y-axis. Here's an x-axis. We should always label these. And we have 63/7 in the x direction. This is 63/17, sorry. We have 63/11 in the y direction. There's 63/11. And we have 63/8 in the z direction. Here's 63/8. Just like before, we want to draw our triangle here. Represent this is a triangle. Lies in the first octant. We want to extend this triangle a little bit beyond what we are looking at in this particular octant. And then make sure to shade to represent that this actually is a solid shape. We don't just have three lines that are just hanging out. So here's our plane. This is a plane that looks like it's sitting in, intersecting the first octant in a triangle and then continuing outward. Alright. Part E says let's find the point at which the line, whose vector equation is given up here, intersects pi. So for our vector equation, it's nice to take this and turn it into parametric equations so that we can isolate what x, y, and z are. So in this case, it looks like x is going to be one constant and two of our parameter. Y is going to be three constants plus -1 of our parameter, so we can just represent that as minus t. And z is going to be -4 constants plus 5 of our parameter. So to find the point at which the plane intersects this line, we want to take the equation for our plane. We can use this linear equation that we have just above here. It would be 17x's, but x is 1 plus 2t. We have 11y's, but y is 3 minus t. And we have 8z's, but the z is -4 plus 5t. Then we need to subtract 63, and that's equal to 0. And again, this feels pretty familiar. This equation here, 17 times 1 plus 2t, plus 11 times 3 minus t, plus 8 times -4 plus 5t, minus 63 equals 0. That's precisely what we did in example 3. In example 3, we got 17/7, 16/7, -3/7, and that's precisely what we should get here as well. What was it again? 17/7, 16/7, -3/7. Oop. And there we have it. All that's left to do is to actually graph this plane in GeoGebra. So let's take a few moments and bounce over to GeoGebra. Here we have this plane all set up, but let's go ahead and take that one out. And we are looking at the particular plane, 17x plus 11y plus 8z minus 63 is equal to 0. Here's our plane. We even actually said that we knew the intercepts of this plane. Just to double check, the x-intercept looks like it's between 3 and 4. And we said the x-intercept here was 63/17. 63 over 17. That's definitely between 3 and 4. We said that our y-intercept was 63/11. 63/11. Oh, it looks like it's a little bit more than 5. That's our y-intercept. That's down here. It's a little bit more than 5. So that looks like it makes sense. Our last intercept, the z-intercept, looks like it's a little bit outside. If we Go ahead and zoom out. Looks like it intersects the z-axis right at 8. Well, we got 63 eighths. 64 eighths is 8, so that's pretty close to 8. That looks like we hit our z-intercept perfectly. So, it's always good to double check yourself. Make sure that this looks pretty accurate. Looks like our sketch would have given us a triangle in the first octant, which it definitely does. Looks kind of like this. There's our triangle in our first octant. Here's our graph, and this is very, very reassuring. All right. So we want to finish this off with just making a definition and then a theorem, just to expand on this definition. This definition says if we have two distinct planes in R3, distinct just meaning they aren't the same plane, then these two planes are called parallel if the planes do not intersect. So in R3, there's no such thing as skew planes. Maybe in some other dimension, but not in R3. It turns out we get two distinct planes in R3 that are parallel if we have normal vectors that are parallel. We can expand on this theorem and say that two planes in R3 intersect, or are two planes that do intersect are either coincident, meaning they are the same plane, or they intersect in a line. In R3, you cannot have any sort of other intersection. They either intersect in a line, or they are the same plane and they intersect each other everywhere. And it turns out that we can actually measure the angle between these planes by looking at the angle between their normal vectors. This is really helpful because we actually have some methodology for finding the angle between two vectors. That's something that we studied in a previous video. So if you ever wanted to find an angle between planes, this is a way to do it. Now, let's finish with this last example. Let's say we have two planes and we know that these planes are parallel. One plane has a linear equation, 3x minus 14y minus 17z plus 14 equals 0. And the other plane has equation ax plus by plus cz minus 4 equals 0. So we know the direction numbers for the first plane, but we don't know the direction numbers for the second plane. Well, the first plane has a vector, a normal vector of 3, negative 14, negative 19. These are the coefficients of x, y, and z, respectively. The normal vector for the second plane is a, b, c. Well, if we have two planes that are parallel, then that means that their normal vectors are parallel. Which means that their normal vectors, if they represent position vectors, would be the exact same vector. If this vector represents a position vector, then, well, A would have to be 3, B would have to be negative 14, and C would have to be negative 19, in order for those to be precisely the same. A is 3, B is negative 14, and C is negative 19. So there we have it.